Here we'll test for measurement equivalence in the program Stata. We're going to set this up initially according to Whittemann's suggestion for testing invariance with longitudinal structural equation models. So this was Keith Whittemann in Child Development Perspectives 2010, and he suggested something for testing, a method for testing longitudinal measurement equivalence. And this is a really good way to do it. There's other ways of initially setting up your configurably invariant model. Todd Little has suggested several different methods. Each method you use, you'll come up with the exact same result. But I like to use this one because it automatically gives you mean differences across time. It's just a good way to set things up. So this is the method that I've used to set this up initially. And in this method, here we have our two different time points. There could be more time points here, of course, but these two different time points, what you have is you set the first time point, the mean of the first latent variable to 0, and the variance to 1. So here in Stata, I can just double click on this and you can see that I've set the mean to 0 and the variance to 1. In other words, this is a standardized variable, mean 0, variance 1. And over here, I've just let this be, the mean and the variance be freely estimated. So mean and variance there are not set to anything, though I have here also said to estimate the mean. So I don't want it to be constrained to 0. If I left that blank, it would have just constrained it to 0 like I have this one over here. But I do want to estimate that mean, so it's going to give me something there. If I had other time points along here as well, they would also be specified just as this is specified, with an estimated mean and estimated variance, those being freely estimated. But the first time point will always be constrained to 0 and 1 under Whittemann's suggestions. Now really you could have any one of, say I have 10 time points here, you could set the last time point to be 0 and 1, and that would essentially then be your baseline. But one of them here has to be set to 0 and 1. Typically we want to see how things change from the first time point, so we set this one to 0 and 1, but it really could be set anywhere. The next part of this is where we set the loading. The first loading here, L1, so we have 3 loadings here on our 3 indicators. So this is a latent variable of father involvement. This is how often, this indicator here is how often does the father encourage the child, how often is the father a friend to the child, act as a friend of the child, and how often does the father talk to the child. You notice we have the exact same 3 indicators here, only this is at age 14 where this is at age 12. So we have our loadings, and we've named these L1, L2, and L3. Now you see here L1, it's displayed up here, and I can change that. That's where I would change these parameters. So again, in Whittemann's formulation for setting up your configurably invariant model, you have the first loading here constrained to be the same across time. So you can see L1 here is named the same thing. In Stata, as in most other programs, you simply name, to constrain something, you simply name them the same thing. So by naming L1 here, naming this path L1 and L1 on encourage, we've simply set those to be the same. And the rest are free to vary. So we have L2 here, and this is L4, L3, and L5. They're not named the same across time, so those will be free to vary. The next part here in Whittemann's formulation is that the intercept is constrained on this first one. So that in the intercept here we have int1. We've named that int1, and you can see up here this is where I've named it int1. So intercept 1, and at age 14 this is intercept 1 as well. Now we have intercept 2, intercept 3, intercept 4, and intercept 5. So in other words, in Whittemann's formulation we simply have here the first latent variable, mean constrained to 0, variance constrained to 1. The first loading constrained to be the same across time, and the first intercept constrained to be the same across time. No other constraints are needed at this point. So this is our configurably invariant model. So I'm going to go ahead and estimate this. I'm going to estimate with maximum likelihood with missing values. This is so it uses FIML or FIML to impute any missing values, or I guess I should say to handle any missing values. So we're going to go ahead and run that. Move this out of the way. You can see here Stata crunching away at the model. It's finished estimating the model. And again, here we have our first loading So the encouragement. So this is F12, F involve 12. In other words, as you can see here, father involvement underscore 12, that's the name of the latent variable on this. And the coefficient here is 0.502, and you can see that that's the same as the 14.1 for encouragement. That's because, again, we've constrained those to be the same across time. Of course, these that weren't constrained are different across time. So the friend here and the friend here, those are different across time, and these are different across time. You can see here we have the mean estimated for father involvement at 14. We don't see the mean estimated for father involvement at 12 because if we constrain things to be 0, Stata won't display it. Stata decides to display those things that are in these models constrained to be 0. So you can see here that it's significant. So it's negative and significant, significantly different from 0. That would tempt us to say, okay, here we have a significantly different, this is the mean of father involvement at age 14 is significantly different from 0. We've constrained our first mean, father involvement at age 12, to be 0. Therefore, this must be significantly different from age 12, significantly less. Though we cannot conclude that just yet, we have to go through the steps to make sure that this is invariant on the strong level. So now what we want to look is we want to look at some fit statistics for this. In order to tell whether or not the weak fits significantly worse than this configurably invariant model, we want to look at a few things. And one of the main things that we look at is the CFI. There's been some research on the CFI to determine what's the cut point. How much does the CFI need to decrease from one model to the next to say that the next model fits significantly worse than the previous model. So let's look here. We're going to go to Statistics, SEM, Goodness of Fit. I'm going to select Overall Goodness of Fit. And we have here Goodness of Fit statistics, and we just are going to request all of them. So here are a variety of Goodness of Fit statistics, and here's our CFI. So we're going to note that. I'm actually just going to open up a little notepad here and say this is our configurably invariant model. So config, I can type config, and I'm going to say that it is 0.997. And I'm just going to keep track here on this. So we're going to eventually be doing a weak model, then we're going to be doing a strong model, and we're going to be doing a strict model. So we'll look at all of the CFIs for those and see how they change. We also want to make sure that we compare the chi-squared statistic. And so I'm going to save the chi-square value by saying estimates store. So I'm going to store these estimates within Stata. We're not going to see them, but they're going to be there. And I'm going to name it something. I've got to name these estimates something. I'm going to name these estimates config. So for our configurable model, I could name it anything, but I'm naming it config just so I can make sure I keep that in my head, that these estimates, including the chi-square value, is stored in this estimates named config. All right, so it did that. It doesn't give me any output to say that it did it, just didn't give me any errors, so I know that it did it. Okay, so now we're going to do our weak invariance model. So we're going to come back to here, and I'm going to clear the estimates that we've had, and our weak invariance models, of course, we're going to constrain all of the loadings to be the same. So here we go to L4, and rather than calling it L4, I'm going to call it the exact same thing as friend over here. So I'm going to say L2. Hit enter. You have to hit enter in there in order for Stata to take it. And then for this one, on talk, I'm going to name it the same thing as talk. So I'm going to name this L3. Now I could have named this L4 and this L5 and kept this L4, L5. It's a little bit cleaner for me this way, but you can name them anything you want to as long as they're named the same thing. So now we have our weak invariance model, and we're going to go ahead and run that. Again, estimating with missing values. And we'll see here the model being fit. And you'll see here now across time on encourage, that loading and that loading are the same. On friend, that loading and that loading are the same, and on talk, that loading and that loading are the same. Again, here's the mean of father involvement, significantly different from 0, but we still can't tell whether or not that's significantly different from age 12 until we move to the strong invariance model. All right, so let's go ahead and look at the CFI for here. And I'm just going to go back here and click on this again. I have all my commands show up on this side. So I'm going to click on this again, and here is our CFI. So I'm going to go ahead and write that down. The CFI in the weak invariance model is 0.998. Now the higher the CFI, the better the model fit. So what we actually find is that by constraining those parameters, by constraining the loadings, our model fit actually improves. Research has found that if the model fit, if the CFI decreases by 0.01 or more, then you'd say that the model has, the next model fits significantly worse, and you would accept the model before. So in other words, if the weak invariance model had fit at, like, let's say 0.97, it would have decreased by by about 2, by 0.02, and then you'd say, all right, the weak invariance model is fitting significantly worse than the configural invariance model. And therefore you'd go with the configural invariance model and you'd say you do not have weak invariance. All right, now let's also store the estimates here so we can do our chi-square test. So we're going to say estimate store. Just click on this again. And now it's going to store the estimates for this model, and I'm going to name it weak. And now we can actually do our chi-square test. And you do that by saying LR test. And our first model was named config. So it's going to go access the chi-square from there to look at it, and then we're going to say weak. So it's going to compare the configural model to the weak model on that chi-square, and there we have it. The difference is 1.04, and the chi-square test is 0.5. The p-value, I should say, is 0.59. So that's not significant. In other words, the model fit doesn't significantly decrease. So by the CFI as well as by the chi-square test, we're not seeing any significant decrease in model fit. So by these indicators, it looks like the weak invariance model fits the data just fine, and we would accept that model. All right, now let's go and test strong invariance. And what we have here is we're going to again clear our estimates. So for strong invariance, we're going to constrain the loadings all across time. So we have int2 and int3 here. So we just need to name this int2 and int3. So click on that, name it int2, hit enter. Click on this, name this int2, hit enter, and away we go. So we can do our estimates, estimate the model here. Okay. You'll see here again it crunching through the numbers. So here is our strong invariance model. And you'll see here that our constants now are the same across time. This one's always been the same across time because we've always had that one constrained. But now we have on friend, this constant, constrained to be the same as friend at 14. Talk at 12, the same. Okay, so I've actually made a mistake here. What I did was, you can see here that this one and this one are constrained to be the same with this. So what happened here was that as I was looking at this, I was changing this, I changed that not to int3, but I changed it int2. So this and this one were constrained, which is of course incorrect. So now I'm going to change that to int3 and go ahead and now those are constrained correctly and estimate the model. Alright, so now we have it hopefully correct. Encouragement and constrained to be the same as encouragement across time. Friend constrained to be the same as friend across time. And talk constrained to be the same thing as talk across time. So now we do have this, our mean, and with them constrained to be equal across time, we can say that yes, in fact, father involvement at age 14 is less than father involvement at age 12. It's significant. This is significantly different from 0. All right? Though we do want to still see whether or not the strong invariance model fits worse than the weak invariance model. If it does, then we cannot accept this model, this strong invariance model, because it fits worse than the weak invariance model. So let's go ahead and look at our goodness of fit statistics again. Here's our CFI. I'm going to go ahead here and note the CFI, 0.996. That is only decreased by 0.002, not very much at all. Certainly not the 0.01 that we'd be looking for a significant decrease. So it looks like our model fits just as well. Let's go ahead and do our estimate store though. We're going to estimate store, and we're going to store these estimates as strong. And then let's do our LR test again. LR test. And we're going to be comparing the weak invariance model to the strong invariance model. And there you see that the chi-square test is non-significant. Again, so in other words, we have not decreased by a significant amount by adding the constraints to the intercepts. And therefore, we really can conclude that, yes, father involvement at age 14 is less than father involvement at age 12. And we could only say that after we'd already gone to this strong invariance model. So let's real quick, we'll go to the strict invariance model, do that one. This will tell us whether or not the reliabilities of these items are the same. So again, go here, clear estimates. So E1, E2, E3. Let's go ahead and name this one E1, constrain that to be the same. And then E2 here, and E3. So I've simply named these things the same across time. I'm going to go ahead and estimate that. Great. Let's go ahead and look at our CFI. Our CFI is 0.99989. Note that here. That's still not a decrease of more than 1. So from the CFI, I would say that we'd probably accept the strict invariance model. But then let's go ahead and do our LR test as well. So estimate store strict. And we do our LR test. Strong, comparing the strong to the strict model. Now here it does say that there is a significant decrease in the chi-square. So we've had the chi-square that says there's a significant decrease. However, our CFI indicates that there's not a significant decrease. When you're run into these situations where the CFI and the chi-square disagree with each other, the chi-square is more likely to reject, is more sensitive to sample size, and will probably reject more models than it really should. So I might go with the CFI instead, though you might also look at the REMC. How different is the REMC? You might look at a whole host of things to see what model fit decreases. There's not been a lot of research on the REMC to say, okay, this cutoff is where you would find a significant decrease in model fit. But this happens often, where you'll have ambiguous, and then you as the researcher get to choose what information you think is most important, and then you just describe that in the paper that you're writing. So you say, I prefer this over that. So that's how you test measurement invariance, or sometimes measurement equivalence, within Stata.